This is a typical compressor performance curve for a centrifugal style compressor. You'll notice that we have lines of constant speed on a discharge pressure or head versus flow chart. On the left side of these curves is what's known as a surge limit. And this is the flow that the compressor can go down to before the internal circulation of gas changes path and it actually tries to run forward instead of being compressed towards the back. So this is a very unstable range to be in. Usually when you surge a machine, it lets you know by having extremely high vibration, extremely high temperatures, and sometimes even higher noise levels than normal. So how do we protect ourselves from surge? Well, a general compressor installation is going to have gas coming in, compressed, going out, going through a cooler and on to the next stage of the process. If the easiest thing is to make sure that your process never comes to this low a flow range. But if you need to have process variability, then what you end up doing is you have what's known as a surge control loop or an anti-surge loop, which is just a recirculation through a control valve that takes gas from the discharge and puts it back into the suction so that it keeps the compressor on its performance map. So if your process normally requires 100 million standard cubic feet a day, and the compressor operates there happily, then it'll just pass 100 million through. If it turns out that your process only needs 20 million a day, but your compressor needs 100, you'll end up passing 80 in the recirculation loop to keep the compressor operating on its performance map. To be able to do that, though, we need to instrument the machine and the process so that we know exactly where we are on its operating map. So we need the pressure and the temperature on both the suction and the discharge so that we know how much head is being developed, and we need a flow measurement so we know what the flow currently is. That goes into what's known as a surge controller, which is usually a black box we buy from a company. And inside that box, all of the performance curves are programmed. And by monitoring these 5 parameters, the surge controller knows exactly where the compressor is operated at any point in time on its operating map. And if it starts to come close to its surge line, then it'll automatically open this valve to protect the machine. Performance considerations. Well, first we're going to start out with a design point. And that one's a pretty good one, so we'll pick that. We designed the machine so that it operates at its 100% speed on that performance point. Since we have a variable speed drive, this could either be a steam turbine or a gas turbine drive. We have the ability to go up to 105% speed. We have the ability to go down to 60% speed. So we can use speed control to vary the machine performance to match the process requirements of the plant. Now, once we've selected this design point, we need to think about some of the potential off-design points that machine may have to be capable of operating at. First one may be, is there a startup gas? For example, on a hydrocarbon plant, some of the procedures are that once you have brought a machine in, either from maintenance or for startup for the first time, that you purge all of the process loops with nitrogen to get all of the air and oxygen out of them. Well, that means that for the first maybe several seconds, maybe several minutes, the compressor will be compressing nitrogen instead of a hydrocarbon gas. The performance of nitrogen is completely different, and so the compressor will operate in a completely different manner than you would normally expect. So by identifying the startup gas up front, we can make sure that the compressor is either sized adequately for operation on a startup gas, or that we know what performance limitations to impose during startup so that we don't exceed the operational characteristics of the machine. Process or equipment drying gas, if they're downstream or if in the process loop there is a catalyst that needs to be dried out, or if there's a refractory that needs to be dried out, sometimes the compressor will be used to pass dry gas onto it, not necessarily the process gas. Again, depending on what gas is selected, it could change the operational map and the operational means of the machine to keep it from going beyond its capabilities. Usually for drying, this lasts for many, many days, so that is a long-term operational consideration. End-of-life gas, either the end of the plant or the end of the field. Mole weights coming out of the ground usually change with time, and if we have a feel for what the end-of-life gas might be, we would want to know that so that we can either plan for it up front or at least make it known to the compressor vendor so that he can add some additional capability into the machine to handle end-of-life gas. For example, if the mole weight is going to be dropping through the life of the plant, and you only need to meet your current process conditions 4 impellers, but at the end of life you may need 5 or 6, the compressor vendor can actually make the casing longer and put blank sections in, which you will then populate with additional wheels as your mole weight drops. So it makes it relatively inexpensive to change the equipment to match the future process requirements rather than having to buy a whole new compressor. Summer and winter considerations, especially if you have a gas turbine and especially if you have large ambient temperature swings, the horsepower that you have from summer to winter can be extremely different, and how you operate your machine and how you size your machine becomes very dependent on this horsepower swing, and we'll get into details on that a little later on. Flow rate changes if your process requirements, if you know that you're going to have large swings in flow rate, then to be able to stay on the operating map, we need to be able to make the map as wide as possible, potentially sacrificing in some other areas. And then balance of plant outages. You may have one compressor that's feeding 4 pieces of equipment that operate in parallel, or multiple pieces of equipment operating in parallel feeding the compressor. Should one of those other pieces go down, your flow rate could change by a significant amount suddenly. And so we need to be able to make sure we can handle those either by speed or by recycle loops during the transient and then get back up operating without recycle again. Now, a lot of those points will help dictate what kind of an efficiency curve shape you're going to want. If you have a very fixed process that doesn't change very often, or when it does change, it doesn't change very far, you may want to have a fairly high peak efficiency to reduce the amount of energy required to do the compression service. And then a high roll-off doesn't affect us because we never operate out there anyway. If your process flow rate potentially could span quite a ways, you may want to have a less high of a peak efficiency, but that it doesn't drop off on as you get away from your design flow rate, which gives you a better overall operational range. Other 2 considerations are going to be field testing. Sometimes we have to test the machines in the field, and that means we either test them on the process gas once the rest of the plant is operational. But of course, once the rest of the plant is operational, the operations guys want it so that they can go ahead and make some money, and so they're not likely to give you a week to do that field testing. So you end up field testing on whatever gas may be around, and usually there's lots of air. And so depending on the field test requirements, we may have to be able to identify how long and how what pressures and flow rates we can operate on air so that we can verify the machine is mechanically sound once it's at the field. And the other is how to start it and how to shut it down. And that sounds kind of silly because starting a machine is pretty straightforward. You push that button and it starts up. But as we're learning on Melny Point, when you have pieces of machinery that are going to be installed to be put in parallel with existing machines, then you have extra considerations. Say you've got a plant that has an existing train of compression, and you want to put in a second train in parallel that shares some of the same process equipment. This new train here shares every separator, and it shares that discharge cooler. With the existing train operational, if you start up the new train, effectively you've doubled the flow rate being pulled out of the separators, and you doubled the flow rate being pushed through that cooler, none of which were designed for those flow rates. So how do you start this train up, and how do you then shut this train down so you can swap load between the two without overpressuring the cooler or potential underpressurizing, or what's worse, start pulling slugs of fluid out of the separators? That becomes an interesting point of consideration when you start thinking about how the equipment's going to operate. So how do you control a centrifugal compressor? You put a valve in the discharge. If you're operating at this point and you got this valve, if you want to have less flow, that means that you want to be able to increase the discharge pressure, which means you have a higher pressure drop across the valve. You close the valve, flow goes down. You want to get more flow, you open the valve up, head goes down, flow goes out, within the limits of the curve shape that you have. But what happens, and this goes back to when we were doing performance considerations, this is the curve that we were told that was going to have. This is the curve that it actually ended up on the test stand. So now we need to evaluate, is this an acceptable curve for us to operate on or not? Obviously, on the old curve shape, we had a very high pressure rise to surge, which gave us lots of controllability by that valve. With this lower rise and almost linear section here, this would be a little bit more difficult to be able to control accurately. Depending on the process that we have, if the process doesn't change very far from this operating point, this may be an acceptable performance curve. If you wish to be able to operate all the way from surge out until your high flow range, if your process will be out at the high flow more than the low flow, you may want to be able to do this because you get more flow you can get more flow with this compressor. But the controllability in this section would be a concern, and we would probably not want to use this kind of a compressor curve shape. It would certainly require a change in the trim of the control valve to accommodate the lower pressure rise that it would see in its operational life. On the other side, what if you have an extremely steep performance curve? Certainly you have very good controllability again with your control valve. But the other consideration with this is we were expecting the maximum pressure to be based upon this flow rate at that speed. And so all the downstream equipment, all the PSV sizing was based upon that pressure. Now we find out that the machine is capable of much more, which may mean that all the PSVs need to be changed. The design pressure of the vessels may be inadequate. And so there are a lot of downstream equipment considerations when we try to evaluate this kind of a performance curve. There is a possibility that you could limit yourself to this discharge pressure in the controls, but that only gives you a very narrow flow range. If your process never goes outside that flow range, then it might be an acceptable curve for you to live with. Now, it's always easy to say, you guys told us you're going to give us this curve, go back and redo it and give us that curve. From a practical point of view, though, you've just spent between 14 and 16 months building this compressor. You're up on the test stand. It's a month before it's supposed to ship, which means it's usually about 3 months before it's supposed to start up. You tell the vendor to go back and start from scratch. He'll do that because he's honor-bound to do that. He's contractually bound to do that. But you're not going to have a compressor for another 16 months. And so that'll delay your start up by about a year. So it's not just a given that if it doesn't come out right, forget it. We're going to tell you to make it new. That's why we need to go in and evaluate some of these curve shapes. These are extreme cases that I'm showing, but you understand, we have to be able to evaluate these and determine from a realistic point of view what we can and we can't live with. The other curve shape we sometimes see is where the flow range isn't quite as wide as we had expected and it just falls off. Again, if we have a very narrow process change this would be an acceptable compressor as far as we're concerned. But once you start getting, if you have to be able to go below this flow rate, you actually have no way of getting there, because you would be closing your valve to build up the pressure rise to reduce the flow until you get to this point, and now you actually have to open your valve up to be able to come down on this side if you needed to get down into this flow range. Now that's not anything that's normally programmed in any kind of control system. This would be extremely unique. The other thing is, at this point of inflection, when you open your valve up, you don't know if the process is going to go this way or that way. So this becomes completely uncontrolled at this point of inflection. So that's why we would say that we would have to cut this machine off at this point and say that's the actual lowest operable flow rate that we could expect out of this machine. That may be acceptable to us, it may be not. If we still need to be able to get to this point on flow, then this machine would not be acceptable. So, some operational considerations. You know, when you've got one compressor in a plant and it takes gas from one place and it sends it off to another place, there's really very few operational considerations, very few startup and shutdown considerations. When you start having issues is when you've got lots of machines which are going to interact in all kinds of different ways. And so this is the CCP up at Prudhoe Bay. Right, currently it has 9 low-stage compressors all operating in parallel, feeding to a common interstage header, feeding 4 high-stage compressors. And this is doing gas reinjection. All the residual gas that's coming out of the facility, out of Prudhoe Bay, if it's not being used for process or for fuel gas, it's got to get put back down inside the well, inside the formation. So these machines, amongst others, do that. Back in the late 70s, early 80s, this machine wasn't installed. So at that point in time, they had 8 feeding 4. And so with this setup, you know, with the centrifugal machines have this typical operating map, and so they were all going to operate at some point of balance on their operating maps. And it's not a bad setup. You've got 8 machines feeding 4. The interstage pressure can float to whatever pressure happens to be the most beneficial for all the machines at that point in time. As seasons change, the interstage pressure would go up or down depending on how much horsepower is available. When a machine has to be brought down for maintenance, as you drop speed, the interstage pressure will change, and the operators would make adjustments to one of the high-stage machines, and you could pretty well control these 12 compressors. Now, I don't know if they covered this in the process section that you've been through, but out of the wells from the formation, you get not only oil, but you get gas and water. And those go into a big vessel called a separator, where they separate out into their constituent parts. And the water gets pumped, it gets put back into the ground, the oil gets pumped for further processing, and the gas you need to compress, a little bit goes for fuel, and the rest of it goes back down into the ground. Now, pumping something, especially water, is pretty well known, it's pretty inexpensive. Pumping oil is also pretty inexpensive. All the money is in how to process gas, and that means that for most facilities, the facility production limit is based upon the ability for that facility to handle the gas that it gets. And so right now in Prudhoe Bay, there are 13, 15, 19 trains that are dedicated just to getting gas back down into the formation in the ground. 819,000 horsepower, that's ISO, that's during the summertime. During the wintertime, that goes up to almost 1 million horsepower that's dedicated to just putting gas back down into the ground. This is really the limitation to all the facilities up there, and therefore, if you want to be able to increase your revenue stream, you have to be able to increase this gas handling ability. Since that is directly related to the revenue stream, those machines are run at max speed, max power all the time. So these 12 machines are operating, low stage machines operating out here at maximum power that's available for the day that they were operating, almost at their maximum speed. And an instrument tech came in and had to do a little bit of work on one of the control panels. And so he went into the control room, opened the control panel, started doing his tests, and unfortunately he crossed a circuit where it shouldn't have been, and so that machine immediately tripped offline. Well, this 12.5% of the gas being put into this header now suddenly wasn't going to be there. These machines were still pulling at the same rate, so the interstage pressure starts to drop. And so all of the high pressure machines started to draw from a lower pressure source. The low pressure machines couldn't make up the difference, so these all ran out on their speed curve because the head rise went up until they finally hit their surge line, at which point that machine dropped offline. Now the opposite case happened. You had minus 12.5% there, suddenly you lose 25% on the other end, the interstage pressure started to go up. So all the low pressure machines which were operating there, now they suddenly ran over to the surge line and it became a race, and the operators lost, and so two of the low pressure machines hit the surge and tripped off, and then that just killed everything. So because of that, this was handling all the gas at the facility at the time. I don't know if you guys have been involved in flare studies yet, but when suddenly all your production comes to a stop, that's a huge flaring event. All the gas that's in the facility has to go somewhere, and if it's not going to the ground, it's going to go to the atmosphere, and it goes out through a flare. So at the time, they had stack flares, and they had one that was for this facility, but it hadn't been sized in case of a complete shutdown like this, and so it got very hot and actually started to melt as it was flaring off this gas. It didn't quite melt all the way to the ground, but it got a good way down there. And so they changed their flaring concepts from a single stack flare to an area flare so they could flare lots of gas without melting in the future. So, but the problem was because of this interstage header that's common to everything. And so to get away from that, we have now installed what are known as tandems, where you have two compressors on a common shaft from a common driver, and they have their own coolers. They do not share an interstage header any longer. So this pressure will be different than this pressure, and it'll float to match whatever the machines are doing. But if, for example, these train of equipment happen to be brought offline or trip, this machine has the same constant suction pressure and discharge pressure, so this machine is not affected as much, and so this equipment is much more tolerant of process changes and upsets than the original setup of 12 was. Axial compressors. If you recall from one of the opening slides, these are extremely high flow machines, very high efficiencies because they do have such high flows. The internal recirculations are such a small percentage. These are up in the high 80s and low 90s percent-wise. They have relatively low pressure ratios. You'll never get maybe above 500 or 600 psi. Right now they're used in air separation plants for LNG. This is what they look like. Lots of aerodynamic blades spinning at a high speed. What they do is they impart, again, velocity to the gas stream, but instead of sending out radially, they send it back axially. There's a stationary blade, which then does a conversion of the velocity from, and it has a pressure rise across it, and also aligns it so that it's ready to be compressed by the next rotational section. You don't get a tremendous pressure rise across each section, which is why you don't get a tremendous pressure rise across the compressor as a whole, but it does handle a very large amount of gas. But also because there are so many of those stationary blades that are so accurately machined, they're very susceptible to foreign object damage, and this is what happens when a little bit of weld splatter in the process pipe breaks loose and comes in and starts bouncing around. One of the other compressors for centrifugals, sometimes used in process, mostly we see it in instrument air, it's called an integrally geared machine. What you have is a motor that drives the shaft into a very large gear, which then spins several pinions at a very high velocity. And so you'll have, these are all a bunch of single-stage wheels that are hung off of the gearbox, so you'll have gas passage into stage 1 and then out again, and through a cooler into stage 2 and then out, and then into stage 3. Obviously, the number of pinions or number of compressors you have is only limited by the number of pinions that you can hang inside this gearbox. We haven't used this kind of compressor very much in process because there's not a tremendous amount of room in the back area here for a good gas seal. This is what they look like in real life. This one has 1, 2, 3, 4 compressors on this side, and there's 4 stages on the other side. So you can get a lot of compression into a compact little package, but here's the compressor. When you start taking a look at all the ancillary equipment that it goes along with it, it still takes up a very sizable footprint. That's the motor driver. Here's the lube oil system for it. And then here's all the interstage coolers for the 8 stages that are hanging off of that compressor. Reciprocating compressors. This is a typical installation. There's the family SUV, if you want to get a proportion size. Synchronous electric motor driving the crankshaft, and then this is a 1, 2, 3, 4 piston, or called a 4 crank reciprocating compressor. These stages do the same, and these stages do the same, so this is a 4 crank but a 2-stage compressor. Production flow is the gas comes into the pulsation damper on the top, flows down through the cylinders and discharges out the bottom. That way, if there's any liquids that happen to form, they have a tendency to drive themselves out rather than build up in the bottom tank until the level reaches the cylinder and causes a hydraulic lockup of the compressor. Reciprocating compression is one of the oldest forms of gas compression. It's been around for a long time. Positive displacement, it has very high efficiencies. It's insensitive to mole weight changes and extremely effective in light mole weight gases. You'll see them, like we said, around hydrogen plants quite a bit. This is a sectional view of a typical recip. The actual part that does the work is out here at the ends. There's a crank shaft that's driven that uses these connecting rods to drive what's known as a distance piece, which is a sliding part that's connected to the actual piston rod, which then goes out to the piston. These are the valves. This is what it looks like. Let's see if I've got a better one. Nope. And this is what it looks like. You've got, you know, a heavily machined, pressure-containing forging with end caps on it for lubrication, and then the crankshaft in the middle. Recips have relatively low flow rates, and they require very large foundations. Typically 5 times the mass of the machine is what we use as a starting point. The reason is that because it's a reciprocating motion, there's a lot of unbalanced forces generated by the motion of the pistons going back and forth, and that has to be absorbed somewhere, and usually the foundation is where it goes. And that's big pardon?
How is the pressure in this compressing? The pressure is high?
You can go to 60,000 psi.
That's pretty high.
Very high. Not 6,000, 60,000.
Oh.
Yeah. For us, we generally would not use them beyond 12,000. When you start talking beyond 12,000, you have very specialized machines known as hyper machines used for some ethanol plant applications. But they're capable of doing that. They're the only compressor capable of doing that. So this is a foundation of some machines we put down in Boca Raton. Huge mass of concrete and then an epoxy grout to bond the equipment to it to make sure that there's no relative motion between the equipment and the foundation. The Boca Raton compressors each weigh 225,000 pounds each. So the foundation was well over 1 million pounds of concrete. We put 8 compressors in there. So that's almost 10 million pounds of concrete. That's a lot of concrete. So, like we said, relatively low flow. Oh, the other thing about recips is that they impart pulsations into the yard piping because the compression is not continuous. It's a reciprocating operation. As the piston pushes the gas, it compresses the gas up to the discharge pressure, and then it suddenly pushes it out into the yard piping. That causes a pulsation, which can cause vibration inside the yard piping. And so to be able to avoid that, we need to do what's known as an acoustic analysis.